So good morning everyone. Yesterday we were talking about different types of mineral additives that we used in concrete. We also looked at some specialty additives which were not really globally available, but they could be made use of as local solutions to the shortage of cement clinker or to reduce the impact of cement clinker in concrete. Okay. Today we will talk a little bit about geopolymers, not too much because I did not really think it was necessary to look at this to a very large extent at this stage. In general, geopolymers are aluminosilicate materials that are activated using alkaline solutions. So, one example of course, we have looked at earlier is the fact that you can improve the hydrolicity of slag or rather the reactivity of slag by using some alkaline activators, right. We saw that earlier that you call it alkali activated slag, alkali activated. But what is happening in this sort of a system, that alkali activated slag is basically using alkalis to increase the reactivity of the slag and introducing the hydraulic properties of slag. For example, alkali activated slag leads to the production of CSH primarily because of the hydration of the slag. However, when we talk about geopolymers, we are looking at some kind of polymerization that happens in the structure of the inorganic materials. So, primarily these are aluminosilicate materials. So, the structure changes by the polymerization of the aluminate and silicate, and that forms some sort of a polymeric chain which leads to the hardening and strength development of these kind of concretes. So, you have examples of aluminosilicate materials like calcined clay, slag and fly ash, but we generally exclude slag from geopolymers because we simply call it as alkali activated slag. When we look at calcined clay or fly ash, we call it geopolymer because there is some level of polymerization that is actually going on. The alkaline activators generally are either potassium hydroxide or potassium silicate, or generally a combination of both potassium hydroxide and silicate, whereas the other kind of alkaline activators could be sodium hydroxide and sodium silicate or a combination of the two. Okay. So, very often you see several research papers that look at only the hydroxide part to try and polymerize the inorganic aluminosilicate molecules. But sometimes what happens is the silica that is available in the inorganic material is not sufficient enough to cause this polymerization to happen in a large way. So, what is really happening is you can add an extra source of silicate to increase the extent of that polymerization. Okay. So, that is why people try to use combinations of sodium hydroxide and sodium silicate that seems to give better results as compared to just sodium hydroxide alone. Now, activation may sometimes need high temperature. Okay. The formation of the polymer chains sometimes cannot be accomplished at room temperature and needs a high temperature. So, generally for the most part when you look at type F fly ash or even calcined clay, mostly what you will see is you will have to perform your initial hydration process or initial polymerization process at a high temperature. The high temperature promotes the linkage between the aluminate and silicate to form the network that results in the polymer formation. I will show you what happens exactly here. So, when you have aluminosilicate sources plus alkali activators, when they are cured either at ambient conditions or at high temperature, okay, what happens is at ambient temperature what you are doing is you are preferring this for systems that have a high amount of lime in them like slag for instance, where hydration of the material actually happens and you end up forming some sort of CSH based products. So, that is basically alkali activated system, but when you do elevated temperature curing you form the geopolymer system where a temperature range of about 50 to 80 degrees is typically maintained for the first 24 hours, or sometimes I have seen research where they have done it for first 72 hours, 3 days. Okay. So, about 50 to 80 degrees moderately elevated temperatures are used to end up forming structures that look like this, So, what is the structure now? So, you have the silicate chain and this is connected with an aluminate and this connection is promoted by the excess of the alkali ions. Okay. Now, what are the alkalis doing? The first step in the process is that the alkalis have to help in dissolution of the aluminate and silicate components from the inorganic material. So, there is dissolution, there is nucleation and then there is polymerization. So, this basic element that leads to polymerization is the formation of the polysilate network. Okay. So, the silate link is what is actually forming in these kinds of systems where you have the silica chains attached with an alumina and this attachment is promoted by the presence of your alkalis. Okay. So, when this link actually forms, this is actually the monomeric link With time, if you cure it at a high enough temperature, you may end up forming this into a polymeric link. That means you have several such links in the chain that leads to the formation of the geopolymer. Okay. So, again there is a lot of literature on geopolymer now. It seems to be the one of the buzzwords as far as research is concerned. A lot of people are working on geopolymer. Of course, what is essentially ending up happening is that there is a lot of controversy whether geopolymers are really useful or not. Okay. One way to look at it is that you are working with a system that does not have any Portland cement. Okay, geopolymers are typically made without any Portland cement, but in some cases you may find that if you add either lime or cement to your geopolymeric mix, you may be able to actually get the polymerization happening at room temperature. Okay. That means at ambient conditions. Without the presence of lime or cement, when you have inorganic aluminosilicates like fly ash or calcined clay, which do not have enough calcium on their own, the reaction will have to be done at high temperature. So, when you do the high temperature curing, you are obviously giving an extra energy input to this process, although the range of temperatures that you apply for high temperature curing is not very high, about 50 to 80 degrees Celsius, but still there is a minor input of energy that you need to give to the system. So, now elevated temperature means giving an extra energy input. So, that is a negative obviously. Second is you are leading to a concrete whose performance is not very well known, because again this is something which we have not looked at in the long term. What is the long term performance? There is research which looks at durability, of course, and there is enough research that shows that concrete with geopolymer based binders has comparable durability to the concrete with regular cement based binders. Now, the positive side of it is that you have cement, rather you do not have any cement in this kind of a system. So, this kind of composite is being made without any cement at all. What does that mean? The CO2 impact of cement is no longer going to be felt when you have geopolymer based concretes. Okay. But please remember one more thing, that we are adding these alkaline activators. Okay. We are adding these alkali activators like sodium or potassium silicate, sodium or potassium hydroxide. The incorporation of these activators implies that there is already a CO2 footprint associated with the production of these chemicals. That is something that you cannot neglect. Okay. Very often you find in research studies that people simply neglect that and take the fact into account that there is no cement in this composite. So, you have to remember that the alkaline solution also contributes extensively to the CO2 emission. And secondly, when you actually handle this material, it is quite dangerous, because the alkaline activators like sodium hydroxide or potassium hydroxide are caustic, they are not very easy to handle. So, you cannot think about this as being done in a regular on-site application. This has to have very special control. So, for precasting, geopolymer may be quite suitable, but for RMC or on-site concreting, geopolymer may not be a suitable solution for cement based composites. So, essentially the hardening happens because of the formation of the polysilate network, which is basically a linkage between the aluminated silicate promoted by the alkali ions. So, again, what are the various inputs for the alkali activated composites? You have, of course, curing process, that is extremely important. First of all, you need to source your material properly. The raw material source should be perfect. Now, in general, what people have been able to come to a conclusion about is the silica to alumina ratio. That has to be maintained within a strict limit. Okay. And that is important because the kind of silate network that you want to form depends a lot on the original aluminosilicate material. It generally is preferred to have a silica to alumina ratio of at least 2:1, okay, so that you get substantial amounts of silicate or silate network forming in the system. So, again in terms of geopolymer concrete, of course, you have the aggregates, coarse and fine aggregates. The aluminosilicate precursor, you need to first grind it to really fine particle sizes, so that there is faster dissolution. Just like cement hydration, the finer you grind your aluminosilicate precursor, the faster will be the dissolution rate. Then of course, you need to transport it to the place where you want to make geopolymer concrete, or sometimes you need to calcine it. For example, when you have clay, clay has to be calcined to make calcined clay or metakaolin to really enable it to be used as geopolymer composite. The activator solutions include water glass, which is your sodium silicate, and then you have your, sometimes you can add sodium carbonate, and definitely you need to have sodium hydroxide, which leads to the very high pH conditions that are necessary for the initial dissolution of the aluminosilicate components to happen. In some cases you may need admixtures or additional water to ensure that you get the degree of workability that you want in the concrete. Okay. So, what you need to do is at each step of this process you need to consider the energy input as well as the emissions in terms of CO2 to really get to gauge the impact of this material on the construction process. So, again it is not very easy to associate the fact that this is a concrete without cement. So, it must be definitely greener as compared to regular cement. You have to do an entire calculation based on the concrete itself and then try to understand whether it is actually producing a significant reduction in the CO2 emissions and energy emissions. Okay. One prominent name that you will come across today is John Provis. He is based at the University of Sheffield, and a lot of interesting geopolymer related work is being performed by John Provis and his group, and that is probably the leading group in the world now that looks at geopolymer research. So, those of you interested in this subject should definitely look up the papers by John Provis. The previous papers that you would mainly see are from a person named Davidovitz. He is a French scientist, and he was the one who had done some early work on geopolymeric systems as applied to concrete. Interestingly, another controversy was created that the pyramids of Egypt, which were built with huge stone blocks, right. What people started claiming is that those are not stone blocks, those are actually geopolymers which have been polymerized in molds and then used directly on site, because they tried to show some examples that the nearest source of stone was quite far away from the site where the current pyramids are. So, they said that okay, no, because of availability of the inorganic materials like clay, people started making geopolymer, and that is what led to the formation of those large blocks. But this theory is not really accepted quite extensively. So, actually there is a site called www.geopolymer.org, which may be interesting for you to go and look at it. The story of the pyramids is also there. Okay. Okay, so generally geopolymer composites, as long as you are satisfying the curing requirements, will end up giving you very high strength early enough. Okay. Especially with slag, the slag based alkali activated systems will give excellent strength at an early stage. Okay. The one drawback is when you use slag for geopolymeric systems or for alkali activated systems, you may end up losing your workability very fast. Okay. So, there is major loss of workability when slag is used. In fact, slag based geopolymer mixes are known to be stable only for about, or known to be workable only for between 15 to 30 minutes. So, that is a serious problem if you are trying to do some large scale concreting. So, what people have tried to do is use combination of slag and fly ash. So, fly ash will slow down the system, okay, and because slag is there, it will continue to hydrate for a long period of time, and the strength will continue to develop over 28, 56 or 90 days. Okay. So, the fly ash basically will end up geopolymerizing, but that may take some time to happen, because of which you can extend the time that you have for workability to be maintained for up to about 45 to 60 minutes. Still not much more than that, but at least 45 to 60 minutes gives you an enough window to do a fairly good precasting operation. So, it is usually suitable only for precast application. For on-site construction, you need to be extremely careful with the kind of operations that you have in place, because the loss in workability is rapid. In Australia, they have actually done some on-site applications with geopolymeric concrete. Again, not geopolymeric, again mixture of slag and fly ash, alkali activated slag plus geopolymeric fly ash systems. So, this is a company called Wagner, which does a lot of construction with geopolymeric materials in Australia. In fact, there was also a company that was formed called Zeobond, and this company manufactures geopolymer cement. So, what they do is they have the aluminate precursor or aluminosilicate precursor and the alkaline activator, which are sold either together or separately. So, for example, you will have a two-part cement, you will have the inorganic aluminosilicate in a bag, and then you may have a bottle of or a jug of the alkaline activator, and then you may be asked to actually mix it in different kind of proportions. Okay. In India also there was a company that was floated recently called Kiran Global, and this company has also come out with a geopolymeric cement. Okay. Unfortunately, the uses and the applications are very limited. People have not been able to show this in a large scale yet. So, there is still quite a bit of doubt about the long term performance of these kinds of systems. In general, from the research papers, what you can get is that the durability performance is usually very good, especially in terms of acid resistance and chloride resistance. Why? Because in regular Portland cement based systems, you end up forming lime, calcium hydroxide, right. And we have talked about this fact earlier that calcium hydroxide is the first to react with the external solutions like sulfates or chlorides or acids, for instance. In the absence of calcium hydroxide and the absence of regular hydrated products like CSH, the components are not as reactive with the components of acids or other inorganic solutions like chlorides or sulfates. So, generally the resistance to chemical attack is generally improved as compared to OPC concrete when geopolymers are used. And the fire performance is also very good, once again because you do not have any lime. So, this calcium hydroxide is what causes a major drop in the performance of cement concrete or CSH plus calcium hydroxide. So, what happens is between temperatures of 300 to 600 degrees Celsius, you have a complete loss of the water from these systems, and because of that your cement paste or cement based systems can actually lose their strength quite rapidly. In the case of geopolymer, you can expect that there is no such hydrated product which is present. Of course, we are talking about geopolymeric systems, not the alkali activated slag systems. When you are talking about slag systems, the fire performance will be quite similar to that of ordinary Portland cement concrete, but here we are talking about geopolymeric systems. So, with slag systems there is no difference with respect to OPC, but with geopolymers you get much better fire performance. Okay. Again, the use of hazardous chemicals, you need to really evaluate it very carefully to see whether it is a viable solution to cement, whether you can actually have the quantities of these chemicals which are required to make concrete on the scale that ordinary Portland cement concrete is made, that remains a big question, and it is not easy to answer that question. So, again when you do it on a lab scale, the chemicals are quite expensive, but when you do it on an industrial scale, it may be possible to bring down the costs. But once again that requires a very careful analysis, and people have not been able to provide that very easily because there is no major large scale applications that have been done. Of course, Wagner has done some airport taxiways with this kind of material, but again the applications are too few and far between to really make a clear estimate of the costs involved. Well, slag based geopolymer systems in the lab we saw we could easily achieve 70 to 100 megapascals without any problems, and this was achieved within a matter of 7 days. So, when you have fly ash based geopolymer systems, if you cure them at significantly high temperatures 60 to 80 degrees Celsius, you may be able to obtain about 50 to 60 MPa at 7 days. That again depends on the kind of mixture design that you adopt. With geopolymer systems, after you finish the heat curing, there will not be much development in the strength. Okay. So, again for heat cured systems, there will be no additional strength development, or rather limited additional strength development after end of heat curing. But for slag based systems, obviously you can imagine that the strength keeps going up as long as there is moisture availability which continues to hydrate the slag. Okay. For slag based systems, the strength will continue to go up with moisture availability, okay, because slag based systems are hydrating, whereas fly ash or calcine clay based systems are polymerizing. And polymerization will stop after a certain period of time. So, heat curing tends to accelerate the hydration of ordinary Portland cement concrete, and there is enough evidence to show that heat curing produces concrete which is generally of a poorer quality as compared to normally cured concrete. But then again, the stoppage in hydration in OPC systems happens because there is no space available for the hydrate products to form and grow. Like we discussed earlier, right, that when mineral admixtures are used, only a certain component of it can actually react, not all of it, because first of all there is lime availability issues, how much lime is actually available from cement hydration, and how much space is available for this hydrate assemblage to actually form and fill up. If there is lack of space, the hydration has to stop at certain stage. Okay, so having looked at different types of additive materials and also looked at some special combinations like geopolymers, let us take a look at certain issues that we may have with additive materials that are used in concrete. The first and foremost is trying to understand the particle size characteristics, because please remember the one of the major advantages of using cement replacement materials is the fact that you can actually optimize the particle sizes to improve the pore filling ability of the cementitious particles. Okay. So, using suitable methodologies to determine the particle size distribution is very important. Quite often when we use a new material, we try to develop a sense of what the particle size are based on either the fineness measurements like Blaine's air permeability, or sometimes we do a sieving test, the amount that is sieving through a 45 micron sieve, that is usually taken as an estimate of the fineness of this material. Now, none of these tests come close to doing an actual particle sizing test. So, particle size distribution needs to be studied using laser granulometry. So, whenever fine powders are used in cementitious systems, you have to use laser based particle size analysis techniques. Okay. Now, having said that, you need to ensure that your system is well dispersed for your particles to be detected quite easily. While that is not really a problem with most mineral additives, when you talk about silica fume, you may have serious problems, because silica fume, I told you already, comes in a condensed form. So, in the condensed form, look at the particle size distribution. The green one is the silica fume, and you can see very clearly that it is much coarser as compared to even your cement. It is coarser compared to fly ash, it is coarser compared to the ultrafine slag. Okay, here this is a brand name for an ultrafine slag, that is basically 53 grade ordinary Portland cement, that is silica fume, fly ash, and you have metakaolin or calcined clay in this case. So, you see very clearly that in the condensed form, the silica fume seems to have a problem as far as laser particle sizing is concerned. You need to develop a technique by which you can actually break these silica fume particles into their individual particles. Only then you can get the actual estimate of the silica fume particles. Please remember, we talked about this earlier, that the silica fume particle has an average size of about 0.3 to 0.5 micron. If you look at this diagram, the D50 for silica fume seems to be around 15 micron, which is not correct obviously, right. It is going to be much coarser than your cement and your fly ash. That is not really what the actual silica fume will be like. So, what you need to do is develop a method by which you can break these agglomerates and then see the actual particle size, because unless you really get an estimate of the particle sizes that are likely to be there in your mix, you can never gauge the impact of the filling effect of these materials very well. Now, this is done directly on the powder. In concrete, what is happening? There is substantial attrition between the aggregates. That attrition usually helps to break down the silica fume particle. And of course, you also have a superplasticizer in a concrete system which can further disperse the individual particles, and that will help you get a better estimate of your overall particle sizes that you can get in the system. Unfortunately, with laser granulometry, you can't do all that. So, you might end up giving a very erroneous information with respect to the characteristics of this kind of material. Now, one aspect that we talked briefly about earlier is the determination of the pozzolanic activity. How do we accurately pinpoint how much of this material is going to react, and what will that reaction contribute to the strength and durability development of the concrete. So, strength activity tests are not necessarily ideal, especially lime reactivity, because lime reactivity is done in unrealistic systems. We talked about this earlier, that you are simply mixing your pozzolan with lime, adding water and simply exposing it to a high temperature with the hope to accelerate the process, but you do not have the kind of alkalis or sulfates that are contributed in cementitious materials. Okay. So, your system is not really ideal because it is not reflecting the actual scenario which happens in cement replaced systems. Okay. Now, when you do the strength activity tests as per the American standards, you are doing this with cement. So, maybe it is a little bit better there, but strength is only one parameter, it is not really telling you the whole part of the story. You are not really gauging any reactivity from that, because strength could be simply contributed by the fact that many of these additives may be acting like fillers. So, you do not really know what is the chemical reactivity which is happening in the system. Now, interestingly, lime reactivity test, that at least from our understanding in our lab, seems to be favoring the calcium based additives. Look at this result here. This is type F fly ash, that is type C fly ash, this is slag, and that is silica fume. Now, lime reactivity test has to be done for fly ash, and as per that, the minimum strength you expect from fly ash should be 4.5 megapascals. So, in lime reactivity test, you make the material, you make the mix and simply cast 5 centimeter cubes which are tested at the age of 10 days after heat curing. So, for fly ash to be qualified as pozzolanic material, it should have minimum strength of 4.5 megapascal. This is failing, type F fly ash is failing, whereas type C fly ash is okay with respect to this. Interestingly, when you do the same test with silica fume, it is failing. Why? Because you need to have certain amount of water in your system that is sufficient to produce a flow. Okay. Many of these tests ask you to add water to the system, which is enough to maintain the same flow as that of a control system. Okay, in the case of lime reactivity test, there is no control system, so they ask you to maintain the flow in a particular range. So, imagine when you have silica fume, obviously you need more water to get the same flow. So, this additional water may end up actually producing much lower strength with silica fume based systems. Already lime is deficient, silica fume, you are adding too much water to the system to increase the flow, you are obviously going to get lesser strengths. With slag, you get extremely good performance with lime reactivity, primarily because there is already an excess of calcium oxide present. So, further you are doing heat curing. So, on its own slag should be able to actually react and produce a much greater strength. So, obviously it is not a surprise at all that you are getting such high numbers in lime reactivity test. The alternative methodologies that people are trying to promote to determine the pozzolanic activity are not very simple. They are based on sophisticated analytical techniques like thermogravimetric analysis, X-ray diffraction. All those are quite confusing to an average quality control engineer. So, quality control engineer can understand strength quite easily, but if you look at other techniques that are used to promote understanding of the reactivity, it is not going to be easy for a QC engineer to execute. So, again that is something which is still not sorted out quite easily. So, we need to arrive at some sort of a estimate which can be obtained first of all quite easily, right, and secondly gives a very valid representation of the extent of reactivity and the filler effect separately in your cement based systems. So, again there are different methods, I am briefly presenting these, we are not going to go into the details of these. You have the strength activity test obviously, and then you have the electrical conductivity method. So, what is happening again when you mix your pozzolan with lime, because of the formation of CSH, your electrical conductivity of the system will continue to drop. So, what you simply do is monitor the electrical conductivity with time and look at the drop in electrical conductivity and define stages of cement hydration based on that. So, this is a classic paper by McCarter and Tran, which is quoted by people who are doing electrical conductivity measurements, which says that the conductivity first has a minor rise, okay, then it starts dropping. This minor rise may be because of ionic species that are there in your cement or cementitious system that start dissolving and increase the ionic concentration, which leads to a enhancement of the conductivity. Then you start seeing a drop, and that drop happens because of the initiation of your hydration reactions. Okay. That drop is quite rapid in this third stage, and what should that correspond to? After the final set, basically that is when your CSH hydration is reaching its peak, or C3S hydration is reaching its peak. So, it is almost similar to your dormant period here. The second period is almost similar to the dormant period because there is not much drop in conductivity in that stage. Okay. And then finally, there is a deceleration stage where the acceleration, where the reactions start slowing down and you start getting a drop in conductivity, but very slowly. So, what people have been able to do is such systems have been able to depict much better the kind of pozzolanic activity that may be there for your systems. Secondly, they have also been able to relate conductivity measurements to the setting time of the concrete fairly accurately. There are several papers in this, you can read this paper, or there are additional papers also available which talk about this aspect. So, using this derivative curve, the rate of change of conductivity curve, this kind of a relationship was proposed for the pozzolanic activity index by McCarter and Tran, and of course, this is just describing what those zones that I have just talked about are. Okay. Again, this is the electrical conductivity test that was done in our lab for bagasse ash. Okay. So, there is lime, that is bagasse ash, and those were mixed in particular proportions. The proportions typically are 8:2 pozzolan to lime ratio. Okay. And then you do a mixing in the Hobart mixer, and that is your, this is the LCR meter which is used to determine the electrical conductivity of a cement paste system. So, the cement paste was actually filled up into this cube and you had electrodes at two ends of the cube, and the LCR meter is connected to these electrodes to determine the conductivity. Now, the problem with the LCR meter is you have to operate it at one particular frequency. So, what people seem to prefer over this is the use of AC impedance. So, AC impedance produces alternating current over a range of frequencies, and you can actually test using that this kind of a system to determine the bulk conductivity of your concrete. So, AC impedance spectroscopy is increasingly becoming a very popular technique as far as construction materials research is concerned. So, again we obtained the same kind of curves for this bagasse ash based system, and based on this we were able to actually predict the pozzolanic activity. So, for example, the as collected bagasse ash, please remember this is the bagasse ash that is collected from the site, that showed an activity index of only 45, whereas the processed bagasse ash, we talked about the fact that you sieve it and then you grind it to 300 square meters per kilogram, and that led to about 52 units of pozzolanic activity. So, again you obtain a better reactivity when you are processing this material. The Frattini test is a chemical test which is performed to see how much of the lime can be bound by your silica in the pozzolanic system. So, again you can go through the details where you basically use a cement based system, 18 grams of Portland cement and 2 grams of your pozzolanic sample are used and mixed with 100 milliliters of distilled water, and then after 8 days at 40 degrees this sample is vacuum filtered through a filter paper, and then you determine the amount of calcium and hydroxyl ions in your solution. Okay. There is a lot of chemistry here, but you can read this on your own. The techniques are described quite well in this European standard EN 1965. Okay. And what you do is you plot on the y axis the CaO concentration and on the x axis OH minus concentration. So, you divide your pozzolanic material into the materials that lie below this curve or that lie above this curve. This curve is basically the solubility curve of calcium hydroxide, and the points that are lying below the curve depict the points that are suitable to be used as pozzolanic systems. So, that is processed bagasse ash here, whereas the other three systems, raw bagasse ash, the coarse fibrous and fine fibrous particles which were removed from the bagasse ash before you do the processing, those are producing pozzolanic activity that is not sufficient. Okay. So, processed bagasse ash consumes calcium hydroxide and brings your overall concentration of CaO to below the level predicted by the curve. Okay. So, a large amount of data was collected by a special RILEM committee that was actually doing testing of the reactivity of different types of cementing materials. So, here there was a range of different fly ashes, slags, calcine clays and all that were tested, and they were able to see that a number of these were actually producing extensively good pozzolanic activity. Now, the problem is this test method is not as sensitive to slags, and it works fine for regular pozzolanic materials, whereas your lime reactivity test seems to be favoring slag and does not work very well for the siliceous materials. Okay, again lime saturation method is simply mixing your pozzolanic material with saturated lime solution, and what you simply do is you measure the lime remaining in solution, because what happens to the lime because of pozzolanic reaction, part of this lime will start getting combined with the pozzolan and the lime remaining in solution can be measured. So, that is essentially what is happening in the lime saturation test. So, once again there is a chemical assessment that is done to determine the extent of lime remaining in solution after you keep the pozzolanic material inside the lime solution for a certain period of time. So, based on this, again the lime that was removed in raw bagasse ash at 3 days is only about 20%, at 7 days it is about 53-54%. In processed bagasse ash at 3 days itself you are almost equal to the 7-day performance of the raw bagasse ash, and by 7 days you have nearly reached 80% removal of the lime from the solution. That means you have got substantially good reactivity even as early as 7 days. So, there are several ways of looking at this. So, you need to form a reasonably good estimate of what kind of reactivity your system will give. Why is this important? Why are we trying to do this? Why not simply make concrete where cement is replaced with fly ash or bagasse ash and study its properties? Why do we want to characterize the initial performance by doing these strength activity based determinations? Why? The contention is that based on the reactivity it shows in the reactivity tests, we can do a much better mix proportioning for the concrete. Now that means what? Better mix proportioning implies finding what? Optimum levels of replacement of mineral admixtures in cement, right. We often do a trial and error method. We say okay, we will do 10%, 20%, 30%, 40%, whichever gives us the maximization of properties, we will use that. But this is just helping us reach there without too many trials by simply understanding the fundamental characteristics of the material and see how much it will be actually able to contribute to the development of your structure in actual concrete. So, all these tests, please remember, are done either on cement paste or mortar. So, the amount of test time and material is reduced significantly as opposed to doing tests directly on concrete. So, wherever possible, if you can devise your test methodologies to work at the cement paste or mortar level, it helps in reducing the extent of time it takes to proportion your concrete properly. ASTM strength activity test is quite good because it uses cement and sand and your mineral admixture, typically in 20% replacement. I am sorry that the water part is going out of here, it's not there in the thing. So, water typically is, so water to cement ratio in, for these kind of for the ASTM based mixtures is typically 0.485. That is the water cement ratio that is typically used for the cement based systems, that is the control system. So, when you replace cement with fly ash or with other mineral additives, right, I told you that ASTM C311 talks mainly about fly ash. So, you usually will replace about 20% of the cement with fly ash. Now, the problem here is when you replace that 20%, you may expect a change in your workability. So, what ASTM tells you is that you maintain the workability by adding either less or more water to get the same flow. That means you are doing this test not at a constant water cement ratio, you are varying your water cement ratio to get the same flow in your system. Now, because of that you may get some differences in performance. Okay. So, generally in fly ash based systems, the fly ash is of a good quality, that means it has got good spherical particles, you may actually end up improving the flow characteristics, you may actually need lesser water for the fly ash based system to work, okay, and that will end up producing an effect on the strength also. So, the strength activity test, again the flow determination is done with the control system and with the blended system, and finally you produce the 5 centimeter cubes and test them for compression. Okay. In silica fume based determination, what you do is replace cement with silica fume, then you add a super plasticizer to the silica fume based system to ensure the same flow as your cement based system. Okay. Silica fume is basically ASTM C1240, that covers the determination of activity of silica fume. Now, there you are actually going to be testing at equivalent water to cement ratio and not at equivalent flow. I mean, of course, you make the flow equivalent by adding a super plasticizer to the silica fume system, and added to that fact, for dispersing silica fume you do need a good super plasticizer. So, it is not correct to do the test without a super plasticizer. So, again this is the result as per strength activity test. For raw bagasse ash, it is much below the requirement of 75%. For the sieved material, I have shown you this before, that we have already reached about 80%, and for the sieved and ground material we were able to reach more than 100% reactivity in this case. Lime reactivity I have already talked about. You mix the lime, pozzolan and standard sand, and lime reactivity is nothing but the strength of the lime pozzolan mixture. The amount of water required to achieve a flow of 70 plus or minus 5% is what is taken for obtaining the consistency of your mix, and at that consistency you make 5 centimeter cubes and test them for compression. Again the exact process is actually shown here, and you show the result in terms of the actual strength obtained itself. Okay. So, some results from lime reactivity tests are shown here. So, this is again part of a large group of laboratories that are involved around the world in doing round robin testing of several different types of mineral additives, slags, fly ashes, type F, type C fly ashes, quartz, calcine clay, several different types of systems are being used in this case. So, here you can see that when you use quartz, nothing is happening. Why? Because there is no reaction at all. Quartz is not reacting with calcium hydroxide, you do not expect any major strength development at all. But when you use any of the other pozzolanic indicators, you get very high levels of lime reactivity from this round of testing. Okay. So, again lime reactivity has been used quite extensively to determine the pozzolanic activity index of different types of mineral additives. Mixture proportioning of concrete with SCMs can also be a little bit tricky, because we talked about this earlier, that many mineral additives are having a specific gravity lower than that of cement. So, choosing to do a mass replacement or a volume replacement can end up giving you very different kind of performances. Okay. So, we need better methods of proportioning required for best performance. We will talk about using these mineral admixtures with an approach of particle packing when we come to the next chapter on high performance concrete mix proportioning. So, again this is something that you need to keep in mind while designing concrete with mineral admixtures. You need to optimize the mixture to obtain the desired characteristics of workability, strength and durability, and for that understanding the aspects we discussed earlier, the actual reactivity, the actual filler effect, that is very important. Okay. So, again we have done extensive study on how to do the initial characterization and produce the kind of result that we need for different types of mineral admixtures. So, this is a very systematic methodology that was developed based on one of our research papers, and if you read through this paper, which I will share with you online, you will be able to get a much better picture of what are the problems ailing the current mixed design philosophies and how we can better improve the approach to characterization of mineral additives and then use them for determination of concrete characteristics. So, to conclude, is there a future without cement? Now, that is something which we keep asking ourselves, whether we can make concrete without cement. The research in geopolymers is getting popular primarily because people want to use concretes that do not have cement. But truly speaking, if you look at the distribution of elements in the earth's crust, there is already a fairly good understanding that cement is optimizing what is actually available on the earth's crust. Why is that? Because cement has silica, it has got aluminum, iron, calcium. These are the 4 major elements in the earth's crust. When you make systems rich in silica and less in calcium, you do not get the hydraulicity from these systems. So, obviously, you need to have calcium based systems as the primary precursor for any hydrating system. Okay. So, cement is possibly an optimized combination of elements in the earth's crust. So, the primary way to reduce the impact of cement clinker usage in concrete is simply to optimize the use of blending materials and also adopt performance specifications. Very often our projects with mineral admixtures do not move forward because they do not allow the use of mineral admixtures based on initial choice of materials. If they look at the performance requirements in terms of durability, long term cost, maintenance and so on, they will find that it is definitely much more profitable to use cement replacement materials. Okay. So, with that, there is a lot of further reading that you can do. You can have a look at some of these websites and also the textbooks that have been published by several different authors. This is a subject that is extensively being studied all over the world because people realize that reduction in carbon emissions in construction or in cement usage or concrete usage is primarily possible only with the replacement of cement with mineral additives. Okay. Thank you all.